Good morning. Well, good afternoon for you, for many of you. Happy to be part of this conference. We all know it's a bit of an experiment, but see how it goes. So I'm going to show you a bit of our work that we do on synthesis, and mainly the part on synthesis where we use large amount of literature extracted data. And again, the motivation for something like this is that in the ab initio field, we've had quite a lot of success at property prediction and compound design. And that's led to an enormous amount of computationally predicted materials, many of which have been made. But there's also quite a number of predicted materials that have not been made. And I show you some examples here. These are out of our own work. Typically, materials that are predicted to be really good lithium-ion conductors or great sodium-ion conductors. The material on the right is a remarkable material. It's a material where predicted magnesium-ion conductivity is as fast as lithium-ion conductivity, even though magnesium is a divalent ion, so highly unexpected. But what these three materials have in common is that even though they're predicted and have reasonably low energy, none of them has actually been made, and it's not for a lack of trying. So I think that leads us to important questions for the field of ab initio theory, is that it's one thing to predict materials, but we really need to understand how we have to bound the design space, and that requires us to know what can be made. Is there some bounding principle on what can be made? And to accelerate experiments, it would even be better to understand even how can you make it? Can we provide a synthesis recipe? There's sort of multiple ways you can approach this problem. You can do this in the traditional sort of scientific way, where you try to understand the mechanisms of synthesis, the kinetic and thermodynamics that take part and how they compete. And I'll show you a little bit of that, but most of my work now has been on trying to understand, can we do very basic synthesis learning by machine learning? And the idea is, of course, that synthesis is a bit of a transfer discipline where people learn from experience, and that experience is embedded in the literature. So the question is, can machine learning pick up on some of that and learn at least basic synthesis? Before I get into that, let me first show you what we actually do on the sort of scientific side. You can actually try to understand what happens, and there's quite a bit of progress in that area as well by our group and others. A lot of that combines theory with in situ observation. So you put a material either in situ TM or much more often in situ synchrotron, so you can in the beamline see exactly what is happening during synthesis. And because the beamlines have such intense X-rays, you can essentially take the diffraction pattern in a matter of a second, so you can fairly rapidly trace the evolution. And here's an example where we're trying to make sodium 0.66 cobalt oxide. It's a so-called P2 phase, that's the target. And what you actually see in the XRD, we start with a precursor of sodium peroxide and cobalt oxide, that the first phase that form is sort of in orange here on the lower graph, is actually an O3 sodium cobalt oxide. So not only is it a different crystal structure, it's actually also a totally different stoichiometry. The graph that's plotted is actually the sort of energy consumption, the grand potential of the system. What you see in that first step, a lot of energy is being consumed. And after that first phase forms, multiple other phases form until it finally, after a really long time, forms the equilibrium phase. And the reason I show this example to illustrate a few common things we have seen in these synthesis experiments is that, one, materials don't just form a crappy version of the target phase and then crystallize it better. What you see here is that there is essentially three other phases formed, well crystallized, before it actually makes the target equilibrium product. And where I think theory has started to gain some evidence that there are rules at work here is that in many high temperature syntheses, what we find is that the first phase that form is actually simply the one that consumes the largest amount of free energy. It's actually the one that has the largest drive in delta G, or in the grand potential more specifically. And once you know what the first phase to form is, you can actually then make some sense of the reaction path, which evolves with much smaller changes of free energy. So there is work on the sort of direct scientific approach to synthesis, but again, what we want to focus on is how do you learn synthesis from the enormous amount of data that's locked up in papers. And so a few years ago, we sort of set out to try to extract this information from papers, because the one thing that's always disregarded about machine learning is that it's really hard to do machine learning without data. And so a lot of machine learning is done on computed data, but there is a bit of an issue there that if you do machine learning on computed data, your gain is limited, right? Because you could already compute it in the first place. So that's why we wanted to go after a problem where the theory is actually hard. So that's where machine learning, I would say, is at its most useful. Okay, so if you want to extract the sort of thousands and thousands of syntheses that have been done in the literature, there's sort of a 4-step process roughly. The first one is retrieval. You have to get access to all these papers. You have to do parsing and extraction of the raw text, because all the text is sort of oddly formatted with HTML tags or other things. You have to find where synthesis is described, which is a sort of rare event because there may be hundreds of paragraphs in a paper and only 2 discuss synthesis. And then the hard thing is actually codifying or extracting the synthesis, and I'll spend most of my talk on this. And then, of course, once you have the data, you can go data mining. So in some sense, what we want to do is go from a paper and a synthesis paragraph, like is shown here, to some kind of codified recipe where it says, specifically what were they trying to make, what were the reagents or the precursors, what are the operations used, and what are the conditions of these operations, right? If you fire, how long, what atmosphere, etc. Content acquisition, I'll skip over because I think I've shown that earlier. We do that in a collaboration with Elsa Oliveri at MIT, where we work on collecting papers together because it's a lot of work. It's a lot of negotiation with publishers, parsing, sort of a lot of boring stuff. And we have about 4 million papers that we have access to now. One caveat, we do not handle PDF sources so far, so most things before 2000 are not handled, and that's because PDF is still extremely hard to parse accurately enough to do science with it. You can do OCR, but it's not nearly accurate enough to do chemistry with, so this is a sort of a problem we are hoping somebody else will solve for us. The way we find synthesis, again, this is sort of a bit of a rare event problem. You may have a lot of paragraphs in the paper and you have to find where synthesis is described. I'll show you how we do that. In principle, you could do that with NLP methods like TF-IDF, which is term frequency, which is essentially a word counting algorithm. It's an algorithm that looks for how frequently some words are used, and it normalizes them by how frequent they are in the documents that you work with. That works reasonably well, but we found that still makes too many mistakes. So we use a combination of unsupervised and supervised learning. The unsupervised learning is an LDA algorithm, and what that essentially does is that it clusters words in topics, and again, that can be done unsupervised. You can just run millions of paragraphs through a computer, and then we identify these topics in sentences. So essentially, on each sentence we read, we put a probability distribution of topics on it. And for example, here's an example, right? It reads words like powders and pressing and pellets, and that clearly are words that come together a lot, and we call that topic pelletizing. But of course, if you do unsupervised learning, the computer cannot express any meaning to that. So once you have a topic distribution over sentences, you can actually then use random forest models to decide what synthesis is. And this has to be supervised. So you need a set of annotated paragraphs where a human tells you what the paragraph says. Is it synthesis, is it not synthesis? And then we go further. If it's synthesis, what type of synthesis it is. And so you can make a decision tree based on the topics you see in a paragraph, what type of synthesis it is. And, this is a complicated random forest, but there's a few times that decisions are made easily. For example, if we see a topic ball milling followed by heating, it's almost always solid state synthesis. So that's an early decision in the decision tree as an example. Okay, so synthesis, we can we can classify paragraphs in papers with very high precision, and we can even classify the type of synthesis. For example, our precision and recall is pretty much always in the 90%, and our precision is well above 95% to classify synthesis, whether it's a solid state or hydrothermal or a sol gel type of synthesis. And this is important because when you do the training later on the extraction of the recipe, it can now work within a certain category. There's a certain way people may describe solid state versus the way they might describe, say, synthesis in solution media. So the most challenging thing is actually the recipe extraction. So now you have the synthesis paragraph, and how do you actually extract a recipe from that? I want to sort of show you that that's quite challenging. For example, let's say you are given this paragraph, or you give this paragraph to a computer. You'll right away see a lot of the challenges, right? So you have to actually identify what the target of the synthesis is, which is often one of the harder things. So in this case, it's GZO. So first of all, you have to identify from the sentence structure that GZO is the target. But now you see a second problem, right? That acronyms are used, and I'll come to that problem. You have to identify that it's made by the precursors, zinc oxides and gadolinium oxide. Then you have to identify the operations, in this case, ball milling, calcining, sintering. And then you have to identify attributes for these operations. In this case, the ball milling was done with zirconium oxide balls, was done in ethanol, and was done at 300 RPM for 20 hours. Calcining was done for 500, that's 500 C for 5 hours, etc., etc. So the reason I stress this is a problem that is much harder than NER or a named entity recognition, because while at some level it's fairly easy to write an algorithm that recognizes chemistry, for example, it would recognize that there's zinc oxide here and gadolinium oxide and zirconium oxide. What is much harder is to write an algorithm that can identify the role that these chemicals play, which is what you need in a synthesis recipe. For example, the zirconium oxide here is not a reagent. It's actually what the balls in the ball mill are made of. Ethanol is not a reagent. It's a dispersion media in the ball mill. So that's what I mean when you have to assign meaning, not just to entity recognition. So the general overview of how we do this, I see that title is wrong. This should say key ingredients. We use a lot of neural networks. So we use two-step neural networks, LSTM neural networks for entity recognition. This is essentially what extracts, first of all, what the materials are and what their role is. We use RNN, so recurrent neural networks, for operation extraction. And then we use dependency parse tree, which is essentially looking at the grammatical structure of sentences to get the attributes of operations. And then acronyms is kind of an interesting one. We use both simple things like tables we make, what we call local and global tables. A local table is simply you keep track of when an acronym is explained in a paper. So that's a very simple thing. Somebody may say, like, I use THF, and then write out in brackets, say what it actually is. A global table is the same, but made across all papers. The problem is that there's a lot of ambiguity with global tables. For example, if I give you the acronym APS, how do you know what it means, right? It could be the American Physics Society. It could be the Advanced Photon Source. There's chemicals that are called APS. It's also the American Physicians Society. And if you Google APS, you'll find there's a ton more abbreviation. So we can decode abbreviations in context, which is what humans do by attention networks. These are things like the very recent BERT models that Google came out with. So these are essentially networks that both use encoded knowledge, but also essentially pay attention to the environment and to context around them, just like a human do. So if I write about that I'm attending the APS meeting, you can probably figure out that that's the American Physics Society, where I'm saying, I'm going to do synchrotron experiments at the APS. That's probably the Advanced Photon Source. And the same is true with chemicals. Okay, so the way we extract the chemistry, right, is with first bidirectional long short-term memory neural networks. The reason that they have to be bidirectional is because of grammar constructions. So the neural network reads the sentence forwards and backwards, because sometimes you say we made X from Y, and sometimes you say I was used to make X. So you see here precursors and targets are in, sometimes precursors come first, sometimes targets come first in a sentence. And they are essentially, again, neural networks help you to see context, right? And I'll show you in a second why that's important. And so they can identify, not only extract the chemicals here that I show, but they can also identify their role. We do a two-step procedure, and which you'll see is important. So first we identify what all the materials are, the chemistry is that appears. And then we use what we call simple language, where we modify the paradigm. We simply replace every chemical with a material. And then that is fed into a neural network to decode the role of that chemical. And the reason it's important is because that way you are not biased by what the chemical is in the role. And I'll tell you why that's an issue with the example of the zirconium oxide I gave you before. If a single pass neural network reads the sentence, skull melting was used in the synthesis of zirconium oxide, it classifies that as a medium, not as a chemical. And the reason is because zirconium oxide is so often mentioned as a medium, a crucible, balls, that neural networks get trained to recognize it as a medium. If you hide the chemistry and you only give the neural network the context of the sentence, then it actually sees that it's a target material because it has here the words in the synthesis of. So we do this two-step procedure to identify what are both reagents or precursors and what are chemicals. Operations and attributes extraction, again, is mostly done by first, again, a neural network to identify the chemicals, and then dependency tree parsing to actually see the things that belong to operations, right? So, for example, heated to 1,000 Celsius for 5 hours. So where are we with this? And I'll show you some data mining. So we now have the largest, I would say, codified experimental database of synthesis reactions. We are done with the one on solid state materials. We have 30,000 solid state reactions. We are working on other type of synthesis. But this will show things like, here's a target material, lithium manganese oxide. You make it from lithium carbonate, Mn2O3, and oxygen in the air to make this material and give off CO2. And it's done in a very simple way, mixing and simply heating to 800C. But if you make LiMnO2, then you see the reaction is quite different. So this looks like the same chemistry, but the valence state in the first one is 4+, and the second one is 3+. Here you start with lithium, with hydrated lithium hydroxide. You make with Mn3O4, and then you make LiMnO2, and this is a little more complicated. You mix, you shape, and you heat at a higher temperature, probably to get the more reducing environment. So we have this for almost 30,000 reactions. We started from about 79,000 paragraphs that were classified as solid state. From about 32,000, we were able to extract solid state reactions, which gives us access to about 20,000 different target materials, because of course some papers are written on the same target material, and using about 3,000 different reagents or precursor materials. This data set is published in Scientific Data, so it's freely available, so you can access it. The data is also labeled with the DOI of the paper it comes out of. Remember, because of copyright, we cannot give you the paragraphs, but you can easily get them from the DOI. So this will help verification and validation of this data set. Okay, so we've done multiple tests on this data. We've done all kinds of automated tests, and then in the end, we did a human test where we take like several hundred reactions, and we have a human check what our precision is in extraction. We do simple things. Is the reaction, can it be balanced, right? If it's if you have reagents that are missing, you'll notice that right away. Are the conditions not too crazy? If something says it has to be synthesized at 10,000 degrees or at 0 degrees, we probably know it's an extraction error. And then in the end, we use humans to randomly test, and that gives us our actual precision. And because we have always aimed to not make this dataset encyclopedic. We did not see it as our objective to extract all possible data, but to make as accurate a dataset as possible for machine learning. We have tweaked all algorithms towards high precision rather than recall. So on targets and precursors, we have very high precision. So we extract the right material that's being made and the reagents. On operations, we have better precision than it looks here. We actually have very high precision. We set up a stringent criteria that if even any operation is missed, then it's wrong. So even with that stringent criteria, we have 86% accuracy. But I would say even for the 14% that are claimed to be not accurate, a lot of the operations are actually quite useful. That you might say miss a mixing step or something like that in the extraction algorithm. Temperature, time, and atmosphere, again, we're close to 90%, between 85 and 90% precision. The media is where we have the least accuracy, but again, that is sometimes because of ambiguity in the text itself. And of course, the media and devices to mix with are often the less important thing. So the dataset should be considered as reasonably accurate. So we are now working on solution synthesis. I think because of time, I'll sort of skip that and I'll skip some of the examples. So I want to show you a few things that we can do with this. You can analyze what are the most common precursors used. Say for manganese oxide, well, it's MnO2, not the manganese carbonate. You can look at the valence distribution between the precursor and the target. This kind of interesting solid state chemistry. But in the last few minutes I want to sort of go a little bit, how can we use this to prediction of synthesis? And the issue, of course, is like, first of all, you have to think a bit, what is a prediction, right? There are two steps of synthesis prediction. The first one I would argue is, can a compound be made at all? And I've come to think that this is not something that machine learning will be able to answer very soon. It's a sort of existence proof. And the reason is that we are missing two crucial pieces of information. We have no negatives in the data set, right? Because people basically don't publish what they attempted and cannot be done. And even if they were to publish a negative, we wouldn't know if that's because the material cannot be made or because they could not make it with their technique. And then we also have no synthesis path information. And this is sort of a topic for longer discussion, but I think that this question cannot be answered with machine learning. So I would argue that the more limited question that one can try to argue is if you assume a compound can be made by solid state reaction, can you predict the precursors? Can you predict the temperature from which you should make it, the atmosphere, the time in the furnace, which tends to be less important. The time is used in fairly broad intervals. And any special conditions, like should you regrind the mixture, should you get it out of the furnace, put it back in, and should you do multiple temperature steps. So I'm going to show you a few quick things like can we predict synthesis temperature? You should think of temperature really as a probability distribution. It's not like a material can be made exactly at 853 degrees, right? It usually can be made in a range of temperature. And so rather than predict a given temperature, we actually predict a potential temperature distribution. And we do that by using all kinds of features from MathMiner, thermodynamics from the materials project, some features related to experiment, like the melting point of precursors, the valence states involved. And then we actually have used various machine learning models, which I don't really have the time to go into. But as you see, the prediction here for very related material, bismuth ferrates, is given in the colored lines of the temperature distribution. And the diagram, the block diagram below it is the actual sort of experimental data. So you see, this is sort of with leave-out cross-validation. We can actually do quite well. And there's sort of an interesting interpretation with the fact that there are two peaks. The first peak is probably the calcination temperature, where you do this loss of CO2, and the second one is actually the sintering temperature. So we can sort of predict synthesis temperature to some extent, although we have not been able to test that in real conditions, right, for real synthesis. Predicting precursors is kind of interesting. The way we do this is that we build a similarity metric for precursors. And the math is a bit convoluted, but the way we essentially do this, we look at what we call similar reactions. These are, for example, reactions that make the same target material. and they might have a different set of precursors. And if you see, for example, a set of precursors where one precursor is substituted, so here manganese carbonate is the manganese source, but in the second reaction manganese oxide is the source, then you know that there's some similarity. So we build a kind of similarity metric between precursors that is adjusted so that we get maximum likelihood of the observation of reaction pairs. Reaction pairs are different sets of precursors that make the same target. And when you do that, you see interesting things. For example, here's a sort of matrix that shows similarity. You know, on the left-hand side is one precursor, on the bottom is another one. And the brighter red the color is, the more they're substitutionable. So for example, if you focus on the top line calcium carbonate, then you see that that's quite similar to calcium oxide. So basically what this is saying is if you can do a reaction with calcium carbonate, you can probably do it with calcium oxide. That's what the data tells us. And that's probably not surprising, right? They are chemically quite related. Calcium carbonate releases CO2 to form calcium oxide. But you see, for example, that calcium nitrate, the third one, is actually also reasonably substitutionable for calcium carbonate or calcium oxide. But then, of course, things like calcium fluoride is never substituted for anything else. And the reason is it's probably way too hard to handle if you don't need to handle it. And it's probably mostly used as a source to bring in fluorine rather than calcium, whereas the other ones are sources to bring in calcium. So you can do this kind of substitution for all common precursors. And now you see where we're going to go, right? We're going to start building new reactions from common reactions by using the substitution metric. So what we do is we build a metric that's based on temperature similarity in reactions and precursor similarity. And we essentially mix that into sort of what's almost a real metric, because there's a Euclidean distance that you can define between them. The temperature distance is the overlap of the temperature distribution profiles. So we mix the temperature and the substitution distance into a Euclidean distance. And so let me sort of skip this. We can now, for a reaction, predict an alternative reaction, right? So if we have a reaction, we can now tell you could also do this with this different temperature or with this different precursor. And we test that with a leave-out cross-validation because that's where we have ground truth, right? So we have reaction pairs, that means different reactions to make the same material. And when we test that, here's sort of the receiver curve. And depending on what we choose as the probability threshold, we see there is a regime in which the blue curve is the true positive rate. So that means we predict equivalent reactions that are actually observed in reality, and we don't have a lot of false positive, which is the red curve. So we seem to have a model by which we can at least predict alternative synthesis routes for a given material. So let me end this, because I'm sorry, slightly over time, is I think I've shown you here an example of how we can use machine learning, first of all, to extract a lot of data that's kind of like locked up and not easily gatherable from papers. And this was a large project. We spent probably about 2-3 years on this now, but the first data set is published on solid-state reactions. The one on aqueous reactions, or in general solution-based reactions, is probably the most important one, which will be coming out probably in another 6 months. And then we can, of course, also use machine learning to do basic synthesis predictions. And I would say this is probably in its infancy, and I've shown you only a few things. You'll find in the slides the references of papers you can read. There's a few more coming out. In particular, the Kononova paper is the one with the data sets, and you can get the same data set online. If you'd like to read more about the sort of scientific approach to synthesis, we just have this paper coming out in Nature Materials, which is kind of a fun paper to read. And I want to thank the team of people who really been working hard on this, particularly people like Wen Sun on the science part, Olga Kononova, who's led the team on the machine learning and text extraction. So, and with that, I'll end here, and thank you very much for all your patience. And if this all works, then by the time this videotape runs, we will actually be able to take questions. Thank you.